Welcome back, everyone. Today, we are diving into an incredibly powerful explainer that serves as a complete masterclass on Raman spectroscopy. We're basing today's journey on a really fantastic, comprehensive lecture presented by Dr. Kim, which breaks down everything from the fundamental quantum theory all the way to the massive, real-world applications of this technology. So, if you've ever wondered how scientists can perfectly analyze the molecular secrets of the universe, you are absolutely in the right place.
But before we get bogged down in the complex quantum mechanics, I want you to ask yourself this fascinating question about non-destructive analysis. How can we uncover the exact chemical structure of a molecule without touching or destroying it? It sounds kind of like magic, right? But it's not. It's just physics. By the end of this explainer, you're going to understand exactly how analyzing the way light scatters off a surface gives us a perfect, totally readable molecular fingerprint.
So, here is our roadmap for today. 1. The Raman scattering effect. 2. Stokes versus Anti-Stokes. 3. Inside the spectrometer. 4. Raman versus IR spectroscopy. And 5. Real-world applications. Let's get right into it.
Section 1. The Raman scattering effect. When light meets matter. To really kick off our journey, we have to look at what actually happens when a photon of light literally crashes into a molecule. When monochromatic light, usually from a super-focused laser, hits a sample, the vast majority of the photons just bounce off elastically. Scientists call this Rayleigh scattering. There is absolutely zero change in energy. Think of elastic Rayleigh scattering kind of like a rubber ball bouncing off a solid brick wall. The ball comes back with the exact same energy it hit the wall with. But Raman scattering is an entirely different story. It is a highly improbable phenomenon. We're literally talking about a 1 in 10 million event. When this incredibly rare thing happens, it's less like a ball hitting a wall and way more like a ball hitting a moving train, where energy is actually transferred between the photon and the molecule. The scattered light comes bouncing back with a completely different energy level. Now, we call this energy transfer inelastic scattering, and the crucial point here is that this inelastic scattering gives us a direct, readable signature of a molecule's internal vibrations and structure. When the laser light hits, the electric field of the incident light interacts with the electron clouds surrounding the molecule. This induces a shift in its polarizability, which is basically just a fancy way of saying how easily that electron cloud can be squished or reshaped. Dr. Kim's lecture notes point out that soft molecules with easily distorted electron clouds, like benzene, are incredibly strong Raman scatterers. On the flip side, hard molecules like water are very poor scatterers, and as we'll see a bit later, that is actually a massive advantage.
Moving on to Section 2. Stokes versus Anti-Stokes, the quantum shift.
Let's break down how this microscopic interaction builds into measurable energy shifts. So when the incident laser light hits the molecule, an electron gets promoted to a temporary, highly unstable virtual state. It absolutely cannot stay there, so it immediately drops back down. Now, in regular Rayleigh scattering, it drops back to the exact same ground state it started from, meaning zero energy change. But in Raman scattering, it drops back down to a totally different vibrational energy level. The difference between the incident energy and this new scattered energy is what we call the Raman shift. And there are two really fascinating outcomes of that Raman shift. First up, we have Stokes scattering. This is where the electron drops to a vibrational state that is higher than its starting state. Basically, the molecule absorbed some energy, meaning the scattered photon actually loses energy and drops to a lower frequency. This is by far the most common form of Raman scattering at room temperature because, well, most electrons are just naturally chilling in their lowest ground state. But then, on the flip side, we have the much rarer anti-Stokes scattering. This only happens when the molecule is already in an excited vibrational state before the light even hits it. It jumps to the virtual state and then relaxes all the way down to a lower ground state. In this scenario, the scattered photon actually steals energy from the molecule, shifting to a higher frequency. It's a much weaker signal, but uniquely, it actually gets stronger and increases in intensity as the temperature of the sample rises.
Section 3. Inside the spectrometer, capturing the elusive photon. Tracking a single shifted photon out of millions of unshifted ones requires some serious hardware and a highly specific path. Step 1 is our laser source. We blast the sample with a perfectly stable monochromatic laser. Step 2 is the sample chamber, which is amazingly flexible, by the way. It can handle liquids, solids, gases, or powders. Step 3 involves our optical filters, which reject all that blinding background light. And finally, Step 4 is the spectrometer and the detector, usually a highly sensitive charge-coupled device, or CCD, that separates and detects the remaining wavelengths.
Along this linear journey, the optical components and filters are literally the unsung heroes of the entire operation. Think back to that 1 in 10 million statistic. If we didn't filter out the blinding light of the elastic Rayleigh scattering, it would completely overwhelm and fry our detector. Specifically, holographic notch filters are used to block the main laser wavelength while letting those incredibly faint shifted Raman photons pass safely through to the dispersive element, like a prism or grating. That element separates them out so the CCD can read the unique spectrum. It's incredibly precise engineering.
Let's look at Section 4, Raman versus IR Spectroscopy, choosing the right tool.
You know, you really can't truly master spectroscopy without understanding its famous sibling, infrared. Both techniques give us molecular fingerprints, but they have very distinct strengths. Infrared spectroscopy relies on the absorption of light and requires molecules to have strong dipoles, meaning they have a distinct positive and negative end, like carbon-oxygen bonds. Raman, on the other hand, detects changes in polarizability and just loves symmetric bonds, like carbon-carbon rings and aliphatic and aromatic compounds. But what's the absolute game changer here? Water. Water strongly absorbs mid-IR radiation, meaning IR struggles terribly with aqueous solutions. It's a mess. But remember earlier when we said water is a hard molecule? That makes it a terrible Raman scatterer. It is essentially invisible to the Raman laser. And that makes Raman the undisputed champion for monitoring reactions in aqueous media or complex biological samples.
And finally, Section 5, Real-World Applications, from micro to macro.
Okay, I absolutely love this story from Dr. Kem's lecture materials, Hendra's rubber duck. Basically, a small toy duck was just placed directly into the spectrometer's laser beam. Almost instantly, the scientists had a crystal-clear Raman spectrum identifying the material as polypropylene, not rubber. This fantastic little anecdote perfectly highlights the ultimate superpower of Raman spectroscopy. It requires almost zero sample preparation, and it completely doesn't destroy the object you are testing. You don't need to dissolve, slice, or chemically alter your sample at all. You just literally shine a light on it. Because it is so versatile and non-destructive, scientists are using this exact method for some truly mind-blowing things across multiple industries. In biomedicine, it's used to detect subtle biomolecular changes, literally differentiating between benign and malignant precancerous human tissues in situ, meaning right there inside the body. It tracks drug binding to cellular DNA and can even classify single-cell yeast and bacteria. Over in the pharmaceutical and manufacturing industries, the ability to measure lower-frequency Raman shifts lets chemists study the crystal lattice structure of drugs. They monitor polymorphism to ensure medications are perfectly formulated, while engineers use the same tech to manufacture cutting-edge semiconductors and assess ceramics. It's everywhere. Which brings us right to our final thought for this explainer. With all this immense capability, if we can detect disease, map out DNA interactions, and verify complex materials just by tracking a single 1 in 10 million scattered photon, what invisible structures will we uncover next? I really hope this explainer has illuminated the incredible power of Raman spectroscopy for you, and leaves you wondering what other molecular secrets are just waiting for the right light to shine on them. Thank you so much for joining me on this masterclass. Keep learning, keep focusing, and I will see you in the next explainer.